Have you ever wondered what the world is really made of? And I don't just mean things like wood or water or air. I mean, what are the absolute most fundamental building blocks of, well, everything? So today we're going to go on a journey, zooming in past everything we can see all the way down to the very heart of matter itself. Let's do this.
It's easy to look at these and see three completely different things, right? You've got solid ice, liquid water, and then this gaseous steam. But here's the thing. They're all just different versions of the exact same stuff. And that stuff is what scientists call matter. To really get it, we've got to go deeper, peeling back the layers to a scale it's almost impossible to imagine.
All right, so let's start with the basics and get a proper definition for this matter that makes up our whole universe.
So what is this matter stuff anyway? Well, the definition is actually super simple. If it takes up space and it has mass, it's matter. That's it. That means the chair you're sitting on, the device you're watching this on, even the very air you're breathing. Yep, it's all matter. And the science that's all about understanding this stuff and how it changes, that's chemistry.
You know these states of matter like the back of your hand. You've got solids like ice, where all the little particles are locked into a rigid structure. Then you have liquids, where those particles can kind of slide and flow past each other. And finally, gases, where the particles are just flying all over the place. And what's wild is that the only real difference between them is how much energy those tiny particles have.
Okay, so when you look around, the world seems, well, complicated, right? There are millions and millions of different types of matter. How do you even start to organize all that? Well, chemists have this really clever system. The very first step is to sort everything into just two big categories.
And this is it. This is the first big decision. No matter what you find in the entire universe, it has to go into one of two buckets. It's either a mixture or it's a pure substance. Let's follow this map and start over on the left side with mixtures.
All right, let's kick things off with a little quiz. What in the world could a can of soda, the air you're breathing right now, and a solid chunk of steel possibly have in common?
And the answer is, they're all mixtures. They're just different things that are physically combined. Sometimes, like with air, everything's blended together so perfectly you can't see the individual parts. That's what we call a homogeneous mixture. Other times, it's super obvious. You know, like cereal floating around in milk, that's a heterogeneous mixture.
Okay, so let's hop over to the other side of our little map. If something isn't a mixture, it's a substance. And a substance is something that has a fixed, unchangeable recipe. Pure water is always H2O. Table salt is always NaCl. And it's when we zoom in on these pure substances that we get to the really, really cool stuff. So, we're zeroing in on pure substances now. But guess what? We can take our zoom one level deeper. See, substances themselves can be broken down into two final groups: compounds and the most fundamental building blocks of all, the elements. Think of it like this. Elements are your basic Lego bricks. You got your red ones, your blue ones, your yellow ones. That's like iron, gold, and oxygen. You just can't break them down any more than that. Now, compounds, that's what happens when you start clicking those bricks together to build something. They're substances made when different elements lock together in a very specific ratio.
And this is where the magic of chemistry really happens. You take hydrogen gas and oxygen gas. By themselves, they're invisible flammable gases, but you combine them in a very precise way, 2 hydrogen atoms for every 1 oxygen atom, and boom, you get liquid water, a compound with totally different properties. That transformation is what chemistry is all about.
We've found the fundamental Lego brick, the element. But can we go deeper? Oh yeah. We're now going to zoom in on a single piece of an element until we hit its smallest possible unit, the atom.
So, back in 1808, this scientist named John Dalton came along with this absolutely game-changing idea. He basically said that everything is made of these tiny, indivisible particles he called atoms, and that chemical reactions aren't some kind of wizardry, it's just these atoms shuffling around into new arrangements. This idea was pretty much the birth of modern chemistry.
Now, Dalton's idea of an atom was pretty simple: a tiny, solid, unbreakable marble. But as our tools got better and we learned more, we realized, whoa, hold on, the atom isn't a solid ball at all. There's actually stuff inside it.
And here they are, the big 3 subatomic particles. Right in the center, you've got your positive protons and your neutral neutrons. And then zipping around them on the outside, you have the negative electrons. And that's it. Just these 3 little guys in different combinations build every single element in the universe.
But what's really mind-blowing is the layout. All the heavy stuff, the protons and neutrons, are crammed into this impossibly tiny, dense core called the nucleus. And the electrons? They exist in this vast, cloudy region around it. It's like a fly in the middle of a football stadium, which means that atoms, and yeah, that includes you, are almost entirely empty space. Wild, right?
Okay, so we've found the atom, awesome, but this brings up a huge new problem. Atoms are unbelievably, ridiculously small. You can't put one on a scale, you definitely can't see one. So how in the world do chemists actually work with them? How do you count something you can't even see?
No, seriously, just think about it for a second. A single tiny speck of dust can have more than 10 quadrillion atoms in it. So yeah, counting them one by one is not going to happen. Chemists needed a workaround, a really, really smart trick. And that clever trick was to come up with a new word for a number. That word is the mole, and no, not the fuzzy animal. Just like the word dozen always means the number 12, the word mole always means this absolutely gigantic number, 6.022 times 10 to the 23rd. It's a number so huge, it's designed specifically for counting atoms.
And this is the payoff. Look at this. You've got piles of carbon, sulfur, and iron. They all look totally different, right? They weigh different amounts, they take up different amounts of space, but, and here's the secret sauce, every single one of those piles has the exact same number of atoms. Each one contains precisely 1 mole of atoms.
So you see, the mole is like this perfect bridge. It lets a chemist weigh something out in the real world, in a lab, in grams, and know precisely how many of those invisible little atoms they're actually dealing with. It connects our world to the atomic world.
So how does it actually work? This is the most elegant part. Scientists have ways of measuring the mass of one single atom. For carbon, that's about 12 of these tiny atomic mass units. Now get this. What do you think 1 mole of carbon atoms weighs? Yep, 12 grams. The number is the same. It's this brilliant shortcut that perfectly translates the invisible world of atoms to the human scale world of grams.
So what a journey! We've gone from the world we can see and touch all the way down to the individual atoms that build it, and we even figured out how chemists manage to count them. But that leaves us with one final huge question. Now that we know what things are made of, how do they, talk to each other? What makes them connect and break apart and rearrange to form our entire universe? That, my friends, is the story of the chemical reaction.